Hi. Today's topic might seem slightly heavy because it involves a lot of jargon and product names, but my goal today is to broaden your horizons in designing applications and introduce you to some of the new options you might have when building your next app. Okay. Before we start, who has worked previously with SQLite database? Okay, quite a few of people. And who knows Tigris, the S3 compatible storage? Anyone? Okay, so you will learn something new, hopefully. My name is Szymon, and I work at Fly.io. But first, what actually is multi-tenancy? A tenant is just a customer and who might have different users. And in multi-tenancy environment, multiple tenants share the same application running on the same operating system, hardware, and data storage mechanism. And the distinction between the tenants is achieved during application design. Thus, those tenants do not share or see each other's data. An example of multi-tenant application is Slack. If your organization connects to its backend services, it's not connecting to a dedicated instance of an app running on a dedicated hardware, but rather to a shared instance used by many different organizations. And this is the app design that segregates and restricts access for users from different organizations. And you can actually read that in the Slack policy linked here. And there are some advantages of running multi-tenant apps. The one that is probably obvious is that it maximizes resource utilization because we make our resources available to multiple tenants instead of having dedicated machines, CPUs, disks run to different customers. It's also data aggregation and mining because you store all the tenants' data in a single database, meaning that you can more easily run queries, for example, to do analytics. And then there is release management. When we deploy changes, we can deploy at once and all the tenants will get the new code. And there are some disadvantages of running multi-tenant application. One of them is that we can get into unfair resource sharing because we can have a tenant that is compute heavy and other tenants might starve for resources. We also have to take care of errors isolation because if one tenant triggers an exception, then it might affect other users of other tenant within our app. And the other thing is that it increases complexity of development because let's imagine that you have multiple tenants and your app has different features that you restrict to different customers based on their plans, and then you have to code. Then you need to develop code for that so that those features are made available to ones and not available to others. But I'm tempted to say that overall, the pros outweigh the cons that the multi-tenant architecture brings compared to running multiple instances of single tenant apps. And what I would like you to consider today is an app design where each tenant is given its own virtual machine, a Fly machine, that runs its exclusive single tenant database hosted in Tigris, the S3 compatible storage. There's probably a lot to that, so let's discuss this shortly, these components one by one. Fly machine is just a VM at Fly infrastructure that runs from a Docker image. The SQLite is a library that implements SQL database engine with the entire TB contained in a single disk file. And Tigris is S3 compatible storage, so it's like Amazon AWS S3. Now you might be wondering, isn't that a single tenant multi-instance app? There is no shared application, hardware, or data storage. So doesn't that just contradict the main advantages, which is the cost savings that come from resource sharing? Not really, since all of since all of the machines are managed as a single fly-up, which is a bag for all the resources the application needs. So the machines, IPs, load balancing, the deployment mechanism. And secondly, these machines have auto start and auto stop capabilities, meaning they would stop if there are no requests coming for a given tenant and start up again when a request arrives. And now, what would be a request flow in such an architecture, considering just a single tenant, as if you deployed your app for a single customer and run a fly up with just one machine for that tenant? So first, you would try to fetch the database file from Tigris. If it's not there, you would create one. And if it's there, you would just download it. You would serve the request, which possibly would mutate the database, send the response back to the caller, and possibly and update the storage into database, and possibly stop the VM if there are no more requests to be served. And now some code skeleton that you would need to get it up and running. So we would start off with creating the database and express object, check if our database is in the storage, then register a callback to send the database file back to the storage, and have just one route to serve, to handle, to run our business logic. And few more code blocks how you could talk to Tigris. So we need to instantiate the S3 client object. For this, you can use the AWS SDK. And the checkDB in S3 function will just issue the get object command for the database key and store the database contents in a local file in a file on a local disk. And the send DB to S3 will do the reverse. So read the file contents from disk and you issue the put object command to store the file back in the storage. To make this code more readable, I skipped the try catch blocks in these functions, but it's actually essential in the first one because the S3 get object command might return no such key error, and then we would default to a new fresh database file. And let's assume we have coded our app for single tenant and we are ready to try it out. So to get it up and running, we need to provision the Tigris storage, the dfly app, and run a machine for our tenant. And the run command, it would create a Docker file based on our project, build the Docker image, push it to the fly.io infrastructure, and then deploy a machine running our image and running our software. But the interesting part is, how do we make it multi-tenant now, since that's just how we start with a single user or single tenant. To understand the idea I'm about to present, we need to reveal more details about how things work in the current form. So when you try to hit our imaginary app, the request will arrive at the closest proxy server, the fly proxy. And at this point, you might expect that the proxy would pick the tenant's machine based on the request. But it's actually not the case here. The proxy will load balance the requests across the available machine. So nothing special here. The proxy doesn't know which machine belongs to which tenant. It will just route traffic to one of them based on some arbitrary rules. And here is where the magic happens. We will equip the machines and our apps with routing logic, enabling them to identify themselves as if they had routing tables. So we can imagine that tenant one machine knows that if there's a request for tenant one, it is responsible for handling it. And if it gets a request for tenant two, it knows what's the ID of its machine and will be able to route it to that machine. And this means that the request can be routed to the appropriate machine if it's not intended for the machine receiving it. And this routing capability is a key component in making our application multi-tenant within this approach. To make it work, we will rely on one of the Fly.io features, which is the fly replay header. And one of the values it can take is a machine ID. So when the proxy sees this HTTP header in response to a proxied request, it replaces the original request as specified by the header. Example, if it contains a machine ID, the proxy will send the original request to that machine. So here is how it works. When a tenant one user makes a request and it happens to be load balanced by proxy to a machine of another tenant, let's say tenant 2, a tenant 2 machine determines it's not intended for it, so it sends a request back with fly replay header set to the ID of tenant 1 machine, and at this point, the tenant 2 machine is no longer involved in handling that request. The proxy receives the response with the fly replay header set and replaces the original request according to the value found in the header. This is to tenant 1 machine, which knows how to handle it. And once done, the proxy sends the response back to the user. Before I show some code snippet, there is one moving part missing. How do we build the routing tables and make the machines self-identify and discover themselves? And we can use machines runtime environment to let it know which tenant it will serve. We can set an environment variable tenant ID when we run a machine, and then we can read that environment variable from inside, as similarly as with Docker. And we can set metadata on a machine to make it discoverable by others. And we will make it discoverable with a dedicated DNS domain that we can query to find machines matching given metadata. And here is an example. We set metadata key tenant ID to value 1, and then inside the machine, or actually inside any machine within that belongs to our network within the app, we can run dig command asking for an IP address of a machine which tenant ID metadata key equals 1. And in the response, we get machine's IP address, and doing reverse DNS lookup, we can get its ID. I guess that to some of you, cracking DNS might not be too appealing, but I do feel excited. But I think that some of you might feel excited about poking around DNS. Anyhow, some code snippets that would demonstrate how that can be actually implemented. I haven't mentioned that so far, but to be able to store multiple database files for different tenants, we need to parameterize the Tigris object keys with tenant ID values. We can do it like that we just include the tenant ID in the path. And then we need one more route. So if an HTTP call matches the tenant ID the machine runs for, we execute our business logic. That's the first route. If an HTTP call doesn't match, then the second route is invoked, and we find the machine ID, providing the tenant ID from the request, and set the HTTP fly replay header with the instance of the machine we want to route the request to. And then when the proxy sees that header, it will send that request to the appropriate machine. And finally, this is the JavaScript version of the nerdy DNS queries we saw a few slides back. And to actually execute them, I used the Node.js DNS package. And we use that special internal DNS domain to query quadruple A records for machines matching the metadata provided in the DNS domain. And finally, we performed the reverse lookup to get the machine's ID from the IPv6 address we got from DNS. And to conclude, I wanted to encourage you to continue your own exploration by giving some ideas that you can follow. So imagine that you have a tenant across the ocean. You can spin off a VM for them, providing a region you would like to deploy to, and the fly replay thing continues to work across continents. So for example, if your Sydney tenant user hits a machine in Warsaw, you can still fly reply them successfully to Sydney. Another idea is that if your tenant has offices on different sides of the globe, you can have multiple machines running for them in different regions. And Tigris will cache the SQLite database files in the regions close to the users and move them according to access patterns. So let's say that somewhere in your tenant machine somewhere in the US will have more traffic, than Tigris will move the object in the background closer to those users. If your application has extreme latency requirements, you could experiment with in-browser SQLite run with WebAssembly and serve the DB files from Tigris directory from the browser. If you can ensure that the file is small enough, it would get replicated across all the regions that Tigris supports. And finally, we could eliminate the static assignment of machines to tenants and treat them just as a pool of compute resources. In such architecture, a request comes in, it just hits random machine, and if it's free, it would fetch the database file and store a log file for a given tenant. That would ensure that when a next request comes, it would see the log file and find the machine that is handling that tenant. And that's it. Thank you. The QR code would allow you to find the full article the talk is based on, along with the GitHub repo. That's it. Thank you.
I have two questions. One is the scenario about having multiple databases in multiple regions for like multiple users. Like, how do you manage synchronization? That's the one question. And the other is why Node.js on DNS side? It seems like far performance for this use case, or maybe didn't I catch something? So that's it.
Okay, so for the first question was how do I ensure that there are no race conditions in accessing the database file? So in the approach with in the example of multi-tenant setup, we would have just one machine running per tenant. So it would be just one place in which the SQLite database is mutated. And in the case when you spin off multiple machines for a given tenant, then there is a risk that two machines could download the file and then you have a write conflict. So to resolve that, you need to use special controls on Tigris. You can simply lock an object. I haven't showed that in the slides, but it's possible to do some sort of locking that we know from SQL databases at Tigris level. And the second question was about DNS. So I wanted to just show how to do it in Node. But yes, you could sort of offload the queries to some other library. Yeah.
Well, but my question is about Tigris, and is it related to LiteFS and Lightstream, the other two projects that your company is creating? And another question is, what's the latency when you're fetching the database?
Okay, so the question is, what's the latency? So the idea here is that the first when you fetch the database for the first time, it will be the highest penalty because it might be in in some remote region, but then it will get cached as close as possible to your VM. So for example, I was running the app in Warsaw, and the closest Tigris Tigris bucket can be in Frankfurt. So if it was originally stored in somewhere in the US, it would get moved to Frankfurt.
Let's thank Szymon one more time for his talk.